So let's take a look at this problem. This is a classic problem. It used to be in every calculus textbook ever written. Um, and then um, it used to show up fairly regularly on AP exams. Not as much anymore. Uh-oh. Ah, there it is. It's like, where's my pen for this? But a variation of this just popped up several years ago, and it was like when people thought, oh, they're not going to do those anymore, and it just suddenly popped up. So let's take a look. So you've got water is being pumped into a conical tank, point down, and for those people who are like, what the heck is that? Well, in the problem that they did on the AP exam several years ago, they used did it like it was a coffee filter, which is basically cone shaped. And they ignored some of the things. So whose radius is 8 meters and whose height is 12 meters. So I'm going to start by, and I usually do it over here in the margin someplace. I'm going to have this conical tank. And again, anything that is constant throughout the problem, I go ahead and put it on the diagram. So this is 8. And I'm not going to put the height down the middle, and you'll see why in just a second. But this distance is 12. Now, water is entering the tank at a rate, so that tells you immediately, you're like, oh, that's one of those d something dt's of 15 cubic meters per minute. Okay, so let's stop there. 15 cubic meters per minute. Cubic meters is a measure of what? Volume. So dV dt is equal to 15 cubic meters per minute.
Do you ever do dRdt for rate?
I don't, because it's like the rate of what? There's several things that are rates. How fast is the water level rising? Oh, we don't have the water level in here. So for the water level, I'm going to use the height of the water level. That's what we're looking for. dH dt equals something when h is equal to 3. Because it wants to know, and I apologize that in the middle of this problem I switched from metric to English units.
I don't think the Brits use feet.
Well, it's mixed.
Your dreams.
All right, so we need an equation, and one of the things that they're likely to give you on the AP exam, although in textbooks they don't always do this, is the equation for the volume. The volume for a cone is 1/3 pi r squared times the height.
Not a very pleasant.
No, it's really not. And part of what makes this difficult is, notice we talk about dV dt, we talk about h, we talk about dH dt. Is r mentioned anywhere in here? No. So you could take the derivative of this with respect to t. You would have to use the product rule over here. But there is a better way. And the better way is to recognize that this would be the radius of your water. And to recognize that r over h, So the ratio of the radius to the height is going to be the same as that of the tank, which is 8 over 12, or 2/3. Solving that for r, we get r then is 2/3 h.
So what if R just be 2?
No, because r and h are not constant. Now, at the time in question, yes. But remember that right now we're dealing with things that are changing. Until we have taken the derivative, we will substitute in no values that are just a snapshot of what's going on at a particular time. Okay? So I'm going to go ahead and replace r with 2/3 h in this. So if I multiply that all out, I get 4 over 27 times pi times h cubed.
So you just multiplied out. You didn't do any derivative.
I've not taken any derivatives. And that's one of the things you want to be careful of. Students frequently will be simplifying, and they've done so much work simplifying, they're like, I'm bound to have taken the derivative at some point by now. Okay, so be very intentional about, I'm in your mind, I'm still just simplifying. I haven't taken any derivative yet. Okay, then when you take the derivative, this is part of why you write it down. Hey, everybody, look, I'm taking the derivative. Write it down. dv dt is equal to 4/27 pi, that's all a constant multiple, times 3h squared times, because I'm taking the derivative with respect to time, dh dt.
So we could only have left it 3h squared if it was dv dh or dh dt.
If we were taking the derivative with respect to h, if we were doing dv dh, then yes, it would have just been 3h squared. And now we have everything that we need. We know dv dt is 15. So that's 4/27 pi times 3 times h squared, which would be 3 squared, times dh dt, which is what we desperately wish to know. The nice thing about this is that's 27. So that divides through the denominator to make 1. So I'll just divide both sides by 4 pi, and I get 15 over 4 pi is dh dt. And that's the exact answer. Now, frequently, they ask you to give a decimal approximation for that, and that's fine. But don't approximate partway through and then do some more work and then do another approximation. You never round off your numbers until the end of the operation. Okay? All right, any questions about that one now? So it involves similar triangles is basically what's going on. I want to show you another example that involves similar triangles.
Will this be on the quiz tomorrow?
No. I'm mean. Gosh.
Quiz is 4.2, right?
Correct. Which is implicit differentiation, if I remember correctly.
Wow. That's not bad.
So let's take a look at this one.
Part 9.6 continue. Wow. I'm so sweaty right now.
All right. So a person who is 6 feet tall is walking away from the base of a street light at a rate of 4 feet per second. It's EN, yeah. Ian if he's really slouching.
Yeah.
All right, so I'm going to go ahead and draw it down here. I don't think I'm going to need a ton of room. So I've got a street light, and it doesn't matter which side you put it on. So that's going to be my street light. And then I've got my 6-foot tall person. And since that's 6 all of the time, I'm going to go ahead and put that number on my diagram. Okay, anything that is constant, you can put on the diagram. Anything that's not, leave it a variable. Okay? And he's walking away from the street light at a rate of 4 feet per second. Well, so that means this distance is changing, right? So we need some sort of a variable for that.
X.
Boring.
It's trusty.
It's trusty, whatever. dx dt.
Never hurts me.
Equals 4.
Yeah. Is this distance getting greater or smaller? Greater. So this is going to be positive 4.
Oh, so he could be going closer, but they're still saying 4 feet, so then it would be negative.
Correct. So you have to interpret that from the problem. Okay? If the height of the street lamp is 16 feet, so this is 16 all of the time, at what rate is the person's shadow lengthening?
What?
So the light is shining past his head and making a shadow on the ground.
But wouldn't it really be hitting the back of his head, and that's what's making the shadow?
Yes. What did I say?
If it's going over his head.
Okay, it's going by his head.
Okay.
I'm going to call this S. You do have to be careful with S's that they don't look like 5s. Okay? So we want to know, what is ds dt? Now, because these are right triangles, occasionally people get mixed up and they try to do Pythagorean theorem on this. But now you're adding something about the hypotenuse when the hypotenuse isn't involved in this in any way at this point. Why would you complicate the problem that way? Right? We know nothing about the hypotenuse's rates or anything, nor do we know about their lengths. But this little triangle is similar to this whole big triangle. Yes, it is.
Oh my God.
Whoa.
So in this little triangle, S is to 6, as in the big triangle,
X plus
x plus s, thank you very much, to 16. You want to guess one of the most common mistakes there? Why I said thank you very much?
They multiply.
Nope. They just do x. They don't do this whole side. Okay? Again, before I start taking the derivative for this, I'm going to cross multiply and simplify this. So this would be 16s is equal to 6x plus 6s. Subtracting the 6s from both sides, I get 10s is equal to 6x. Taking the derivative now with respect to t, I get 10 ds dt is equal to 6 dx dt. And my only unknown in that is ds dt. So that'll be 10 ds dt equals 6 times 4. Divide both sides by 10, and I get that ds dt is 2.4 feet per second. Okay? So both of these problems had similar triangles in them. One of them, the similar triangle, was the equation. In the other one, the equation was something else, and we had to use similar triangles. So similar triangles do come up in some of these. Okay.
Did they give you most of the